Okay, picking up here on the same slide where the last video left off, I just want to reiterate, this is the primary thing that I want you to focus on from this chapter, is being able to look at a structure and kind of count how many atoms are present in the structure, again, based on where atoms are. Now, we'll see it's going to get a little more complicated than just corner, body, or face. There are some other places where atoms can kind of end up in a structure, but this is the primary thing we want to look at. I want you to be able to see a picture of a unit cell and tell me things like what is the formula of the material, like what's the ratio of the cations to anions, maybe what is the charge on the cation, which you could get from identifying how many anions are present relative to the cation, that sort of thing. That's primarily what we'll see in the kind of at-large problems in the second worksheet for this chapter. The first one will be more problems from the book, so that'll focus a little bit on some of the geometrical issues that I'm going to let you kind of work on yourself there as you work through the material in the chapter. But for that kind of second assignment, right, it's going to be analyzing this type of structure. Now, with that in mind, let's go on to the next slide. We can take one of these structures and sort of fit in other atoms as well. So if you start to mix together different types of atoms, you get a compound called an alloy, and really two different types of alloys to think about here. A substitutional alloy is one where the second element kind of takes the spot of the first element in the structure, and that's this first picture here. Where we have gold and silver. Gold and silver about the same size, so you can mix gold and silver atoms together. And you can see in the picture there some of the silvers are kind of just plopping into that face-centered cubic structure where a gold atom would be. So they're substituting in to that position. The other type of alloy is called an interstitial alloy, and this is where you add an element that is usually significantly smaller than the primary element in the compound, and that element can still fit into what would be an empty space in that particular lattice. So in the second picture there for an interstitial alloy, this is steel. So it's primarily made up of iron, but you make iron into steel by adding carbon. So carbon is pretty tiny compared to an iron atom. You can see the sort of black colored balls for carbon there actually fit right in between the irons, and that causes a change in the physical properties of the material. So iron is heavier and is not as strong as steel, so by adding in some carbon you actually make the material stronger and you actually make it lighter as well, so you can have a great effect on the physical properties of the material. Okay. Now, that's a little harder for us to evaluate in terms of unit cells, but we should be able to identify those two different types of alloys. But where we are going to be able to analyze space again is when we get into ions. So ions are made up of two different types of components, or at least two different types of components, the cation and the anion. What we want to think about is how can we think about where the anion is versus where the cation is in the structure. And there's three basic structures. They're listed over here on the left side, but I'm going to zoom here in a second to talk about these structures. There's three different basic ways we can think about ionic solids. So in all of them, it's helpful to think about the anions as making up one of the lattice structures we talked about. So in the first picture here for cesium chloride, we've got chloride ions as a primitive cubic unit cell. So chlorides are on the corners. Well, the cation's got to be located in there somewhere. In this case, the cation cesium is located right in the middle of that structure. So it's in what would be the body center of the structure. But since this is ionic, we describe that a little differently. So we describe this structure as that cesium in the center is surrounded by a cube shape of chloride anion. So that is called a cubic hole within the lattice of the chloride. So another way of describing the cesium chloride structure is cations residing in a cubic hole within the anion lattice. In the middle here is sodium chloride. Now the sodium chloride structure, again, chloride anion is the larger structure here. The larger chloride anions are on the corners here, but also on the faces. So this is essentially a face-centered cubic arrangement of chloride anions, and then the sodiums are going to have to fit into that structure. So in this case, the sodiums are fit in along the edges of the cube, in between the chlorides, and there would be one sodium right in the center of this cube as well. And if we kind of think about what we were talking about on the last slide, chloride, corners and faces, that would mean there's 4 chlorides here. 8 times 1/8 for the corners, 6 times 1/2 for the faces, for a total of 4 chlorides in the unit cell. Sodiums are on edges. Well, that edge is shared by 3 additional unit cells beside the one we're looking at. So each edge, 1/4 of that sodium cation is in that cell. There's 4 along the top, 4 along the bottom, and 4 along the side. So there's 12 edges in a cube. 12 times 1/4 would account for 3 sodiums. Now we know the structure of sodium chloride is NaCl. There's 1-to-1 ratio. The 4th sodium is right in the center of the unit cell. Now, this is described as sodium chloride structure, or rock salt structure, but the other way to think about it is that each sodium is fitting into what is an octahedral hole within the lattice of chloride anions. So every sodium is surrounded by an octahedron of chlorides around it. The last structure, zinc sulfide structure, we have a face-centered cubic arrangement of our anions, sulfide in this case, sulfur. And the zincs in this case, it's a little harder to see here. This may be a case where you want to look at some of the pictures in your textbook to get a little better idea of what is being described here. But the zincs in this case are in what are called tetrahedral holes within the sulfur lattice. So this zinc right here, you can see, you may not be able to see quite as well, but there's a tetrahedral of sulfurs surrounding it. So every cation has sort of a tetrahedral arrangement of anions around it. There are actually twice as many tetrahedral holes in there as there are anions in this lattice. So this is a common structure for an ionic compound with a 2-to-1 ratio of cation to anion, or anion to cation, depending on how you define your lattice.